Thanks. Hello? Oh. Yay, Zoom. Hello, to those watching in the future, I'm David. I'm the coordinator of the Maths Learning Centre. It's semester 1, 2021, and this is a revision seminar for multivariable and complex calculus. I've had a couple of requests already, and if I get through those, then I might talk about other things as well. So I've been asked to begin with some integral stuff. So the things I've been asked to talk about are a change of variables, and also just setting up the integral. Okay. All right. Give me a moment to process those. All right. Both of these require us to hold on to the same thing, which is that success with integrating requires us to locate every point in the object that we are integrating across. And the fancy word for locating every point is parameterization. Okay. And I've got to be more specific about that. When you locate every point, you have to have, if you've got a two-dimensional object, then there's going to be two numbers that when they change will move the point on the surface. A three-dimensional object, there'll be three numbers that when you move them, it will move the point within the volume. And with a one-dimensional object, it'll be one number that when you move that number, it moves the point within the curve. And so if you've got a curve, you'll have numbers t that will tell you points on the curve. And as you move this number, it'll move the point on the curve. And therefore, locating a point on the curve comes down to choosing the correct value of t. But if you've got a surface, that will require you to have two numbers. So usually those numbers are arranged in a plane, but it doesn't have to be. They can just be two separate numbers. You know, often they're called U and V, I think. And this combination of those two numbers will produce the point on the surface. And as I move this number, then this point will move. If I move this number, this point will move. They'll move independently. And if you've got a volume, then there'll be three numbers that are needed to figure out where you are. Okay, that's the big idea. Right, there may be, here's the thing, there may be more than one way of locating a point in this surface, or in this volume, or in this surface, or on this line, and that's what causes a need to change your variables. All right, cool. I'm just thinking. Yep. Okay. So the second thing is that you need to think of what quantity it is that you are going to be accumulating across the object. So when you integrate, integration is accumulating a quantity. And when I mean accumulating, I mean doing a running total. You keep adding it up and you get more and more of the quantity as you cover more and more of the object. So the idea is that you have some object and every point on that object is associated with a number. And you basically add up all those numbers, taking into account how much time, how much space it spends being that number. How much? Spend is the wrong word, but it's close enough. So what I mean by that is, if I was in R2 and I had a region like this, and every point in this region had, say, I don't know, a temperature, and so maybe it's 5 here and 10 here and -6 here, and if I only move a little bit, it's quite close to the temperature that it is nearby. That's how these functions work. And maybe it's 6 here and 20 here and 30 here, and every point has a number. And then I look at this shape and I go, what I'm going to do is I'm going to add up all those temperatures, taking into account how much space they spend being that temperature. And so like, oh, it doesn't spend much space being nearby to 10, but it spends a lot of space being nearby to 6. And take all that into account, and that's what you get when you do an integral. So yeah, so this would be, you know, the double integral of, this is the temperature dx dy across the region, something like that. And so this dx dy is multiplying the temperature by the amount of space it's taking up, by the amount of space that is that number, the amount of space that has that number attached to it, and then we add them all up, and that's what the integral is. Okay, so you have to choose what it is that you're accumulating. No, there is no and. You have to choose what it is you're accumulating. Okay, those are the two things that go together, and it would be more obvious if I just do an example. Yeah, right. So I'm actually going to do the setting up an integral bit first, if that's okay. I'm just going to write this one down. Those who are on the Zoom can't see it yet, but I can't be bothered switching my sharing. So I'll just write it because I want to do it live anyway. Okay. Solid ball has a hole. Through the center. A hole is a circle. And the length of the hole is 2. And of course it's 2 inches because, you know, we're barbarians. Use a double integral to determine the volume of the wood drilled out. Okay. Just going to leave it at that. This is a classic multivariable calculus problem. If you just search for multivariable calculus hole in ball, then you'll find it online. Classic. Okay. So I'm just going to try and, we've got a ball. Oh, do we have the radius of the ball? Ah, because it's, yeah, okay. We have a ball. And we have a hole. I wish I brought my Play-Doh. Like that. Oh, okay. So I'm just going to imagine, what if my ball was really small and we ended up taking like most of the ball, because then that would be like chopped off like that, wouldn't it? Right. So if I look at it from the side, I'm just imagining at the moment. If I look at the ball from the side, it was like that, and then I drilled a hole through it, and so that bit at the top gets cut off. And so from the side, it'll look flat at that spot then, won't it? Okay. So I have to figure out how to do this volume. All right. So what am I going to accumulate to figure out this volume using an integral? I can literally just figure out this volume using cylinders and stuff, but they told us not to do that. And they don't want this bit, they want this bit, don't they? They want the bit that was actually removed. And that's just an area, but they want the volume. It's going to be like a... that thing. Okay, I now understand what it is. So it seems to me that if I want to make a volume, like if the answer I want at the end is to be a volume, then I'm going to need to accumulate areas across, accumulate heights across an area, and that should produce a volume. So if I imagine stacking up a whole lot of little stacks like this and stacking them all together, that will produce the volume. So if I could create a function that told me how high this was, then I could use this circle here and integrate across that circle. That's my guess for what I'm going to do. Yep. Okay. So, all right. So now I have to locate every point in the thing that I'm doing the integral over. It will help to locate every point on the sphere too, so I'll do that as well. So I'm going to let the radius of the sphere be r, so that I can create an equation for the sphere itself. And I'm going to make the equation of the sphere be that. Because being of radius, this is the distance from the center, and that must be equal to r squared. That's my guess. That's the equation of a sphere. And so that means that the height of the sphere among them above the middle there ought to be like that. We'll take the x squared and the y squared and do the square root, and that'll be the top of the sphere. Oh, wow. Fun. Yeah, that doesn't make any sense, does it? Okay, we'll get there. So I could do this. I could say that now this is the height of this curved part of the top of the sphere above this circle just there. So on the circle, this circle, which has radius r, the height is this. Oh crap, I've called it capital R now. I will call it capital R, sorry. And so I could do the height, the thing I'm accumulating is height times the amount of area that goes with that height, which is the dx dy, and integrated across this circle, which I shall call C. It's supposed to be a disk, isn't it? Oh, damn it. When you say circle to a multivariable calculus lecturer, they think you mean just the edge, so I'm going to call it a disk. Because to a multivariable calculus lecturer, a disk is the filled-in circle and a circle is just the edge. So that would be an answer, which looks like it would be very difficult to do. Yep. Okay. What if, so that's fine. This is what I have to do. This is well, at least half the volume anyway, because this is just the top half, because I haven't gone downwards as well. So the actual volume is going to be the top half. And so the actual whole volume is going to be 2 of that. How are people feeling about what I've just done? Yep. Because this is the top of the sphere because I took the plus square root, which means it only tells me how high this is. And so I've got this base times this height, which will give me the top half. And I haven't done the bottom half. Because I've made the center of the thing where z is 0. How are you feeling? Mm-hmm. Do you want to tell me more about that? Okay. This is for all of you, so you need to tell me things. So one way of making a volume is to accumulate heights, stack up a whole lot of tall heights all together in a clump across an area. I'm literally in my head thinking of a whole lot of blocks that are stacked up. And I'm adding together all the heights of those blocks, of those stacks. And I need to figure out how tall the stack is, and that height of the stack is this height here. It's the volume of the cutout. Like this would be the volume of the whole sphere if I used all of this circle, but I'm only using this bit because that's the cutout bit. I haven't figured out how big that is yet.
So how would it fit into
this disc would be bigger, but it would look exactly the same. But I haven't yet figured out how wide this disc is yet, so I don't know. Oh crap, the capital R would be the whole sphere, wouldn't it? Oh, for the sake of Frel, David. This is a little r. Gotcha. Which we don't know yet. Yeah, big R for the square root because that's for the whole sphere. And then I'm going to let the radius of the whole be little r. Let's do that. Sweet. Well done. So if it was a big R, that would be the whole bottom of the sphere, the whole middle of the sphere, but little r, like the sphere is here, and that's big R there. That was a very excellent question to get to the heart of what the problem was. Okay. Cool. So they will look the same. If this disk was that whole thing, it would be the volume of the sphere. If this disk is that bit, it would be the volume of the bit that I cut out. Well, half of it anyway. Okay, so now I need to figure out how to locate every point in this disk. Oh, damn it. Can I just make it R sub H, R for the whole? There we go. Okay. Cool. So I need to locate every point in that disk that is the hole that was cut out. All right. All right. We'll get there. I know that the easiest way to create a circle is with cos theta and sine theta. So I'm now going to focus entirely on this disk and create that point, points inside that disk. So to locate every point on the edge of a circle, I could do the radius times cos theta and sine theta. That would be the edge of the circle. This is not going to turn out to the way they did it, I'm sorry. So the edge of this circle, a circle would be cos theta, sine theta. No, I will do it the way they do it. A circle would be cos theta, sine theta for theta between 0 and 2 pi. That would produce every point on a circle. But my circle is radius RH, so it'll be, the edge of this will be RH times cos theta and RH times sine theta because it's that much wider. But I want to locate every point on the inside of this circle, not just on the edge. So I'm going to pick a point. It's going to be R from the center and it's going to be theta around. And so every point on the circle will be now, every point inside the circle is now this, R cos theta, R sine theta, for theta between 0 and 2 pi, and R being between 0 and whatever the radius of the hole is. That locates every point within this circle. All right. So remember how I said I had to figure out what it was I was accumulating, which was the height. A height times a height accumulated across an area will be a volume. And I have to figure out where every point that I'm accumulating it across, which is what this bit is. Okay, so now the disk can be described by running through all of these numbers, all the numbers from 0 to 2 pi and also all the numbers from 0 to RH. Cool. All right. I'm hoping that I'll get something useful eventually, but we'll get there. And so that means that these numbers are going to be what's on these integral signs here, but that doesn't match what this dx and dy are, so I'm going to have to switch them to being about r and theta instead of x and y. And that's where this change of variables comes in. So I know that x is r cos theta, which means that dx on dr is cos theta and dx on d theta is minus r sine theta. And I know that y is r sine theta. So dx on dr, dy on dr is sine theta, and dy on d theta is r cos theta. I believe that you're allowed to shortcut this and just skip to the answer for this particular parameterization, but I can never remember it, so just want to show where it came from. And so the Jacobian is this matrix. So I've got dx on dr and dx on d theta. No, that's what I'm thinking about. Dx on dr and dx on d, and damn it, it's the other way around. Dx on dr and dx on d theta, dy on dr and dy on d theta. It doesn't really matter if we had it around the wrong way. The determinant is the same anyway. And so that would be cos theta times r cos theta would be r cos theta squared minus sine theta times r sine theta minus r sine theta, which will be that. And so I've got r outside of cos theta squared plus sine theta squared, which is r. Yay. So I started with creating the points. Every point in this disk, its x coordinate is this and its y coordinate is this. And I've differentiated those to produce this matrix, and it comes out to R. So I believe that in your course notes, it says that if you set up this parameterization, then it's automatic that this is what the Jacobian will come out to be. It'll just come out to R. And that means that a change in dx and dy, a change in the product of dx and dy will be the size of the Jacobian times the change in dr and d theta. That's how change of variables work that we were asking about. That the product of the little change in x and the little change in y, because that idea of dx dy is thinking that if we're at a particular location and we go a little bit in x and a little bit in y, how much area are we going to pick up when we make both of those changes simultaneously? That's the dx times the dy. But we're saying, well, how is that related to how much area we'll pick up if we change the radius and the theta a little bit? And that's what this is trying to get a handle on. So that's that. So I can now replace this dx dy as a dr d theta. But my formula is still in terms of x and y. So I'm going to need to replace that in terms of r and theta as well. Well, x squared plus y squared would be, if we're going to do it the full version, so we're going to get r squared sine squared, and cos squared plus sine squared is 1, and we'll get r squared. And so now we have that everything can be figured out. So now r squared minus x squared minus y squared is r squared minus little r h. No, just little r squared. All right. So now our integral to cover the whole of the disk I was thinking of, I need the theta to go from 0 to 2 pi, and I need the radius to go from 0 to whatever the radius of the hole is. This formula is now, and this is r dr d theta. That's what this became. Yep.
So x squared plus y squared equals what? So is the integrand x squared plus y squared?
No, I mean the integrand has got this crap here. I just saw a minus x squared minus y squared, which is the same as x squared plus y squared, all minus.
Yeah. But why is that then the radius? Oh, that's the radius of the
It's the radius of the position that I'm at. So little r is how far from the center I am. And if I'm x this way and y this way, then x squared plus y squared is r squared from that little triangle just there. How do you feel about that?
It's just an identity.
I'm saying that if I locate a point with its x coordinate and its y coordinate, and I want to know the radius of that point from the center, then because of Pythagoras' theorem, x squared plus y squared will be r squared. because this is the x coordinate there, and that's the y coordinate there, and that's the radius there.
So that's just trying to connect the R with the x and y.
Yep. It's deliberately exactly that, trying to connect locating a point using x and y to locating the point with r. And since I'm going to do this integral by locating the points using r and theta, I have to change this formula to not be involving x and y anymore and involving the r and the theta that I'm using. So that's the goal. Like, I figured out it was really difficult to locate every point in this disk using x and y. So I'm going to locate every point using r and theta, which means the formula needs to be saying, based on the r and the theta that I'm using to locate this point, what would the formula be then? So I'm replacing the x with something involving r and theta, and the y with something involving r and theta. And it turns out that this x squared plus y squared simplifies to r squared. Turns out to be that as the formula. Doesn't have a theta in it at all, which is convenient. How are we feeling about what's happened here? This move was not made clear in the solutions that I was looking at. Yeah. So I'm pretty sure that you are allowed to skip all of this working and go straight to the Jacobian is just r in this context. Yeah. Because this is one of the classic parameterizations of a disk. There are others, but you'd have to figure out the Jacobian yourself for those, which is why it's a slight advantage to use the classic ones. So this integral would now have to be done, and I would now have to do this integral the way that you do double integrals. Would anyone like me to do this integral? Okay, cool. So I can now work my way in or out. I can see that this bit doesn't involve any thetas. So I can bring that thing is a number, and I can bring that whole thing outside the integral. Just to make it absolutely clear what just happened. That just makes it a little easier to do the integral because I don't have to worry about the other one. And now I can do those two integrals separately. I notice that this is nearly the derivative of this, so I would do that with ordinary substitution like I did back in Maths 1A. Oh, cool. Can I bring this 2 in? Because there's a 2 here. Yeah. Gonna. No, no, I won't. I'm just going to deal with it. So I can see the r dr. It's minus a half of du. This is root u. And so I've got, and r equals 0 would mean that the u would be r squared. And r equals rh would mean that the u would be whatever r squared minus rh squared is. Ugh. So that became a u, that became minus a half of du, and now I've got this integral, which I don't like particularly, but there we go. That's the same as u to the power of a half, so the power would go up by 1. to 1.5, and I divide by the new power. The minus a half is multiplied on, so it'll still be there. And I'll have u equals r squared and u equals r squared minus rh squared. And that doesn't look fun at all. Okay. I guess that becomes minus a third. Wait. Just a second. We haven't used the fact that the hole is length 2. I reckon I can possibly use that to help. Just a second. Wait. Where's my diagram? This is 2 here. And this is the RH. New diagram, just a second. This is 2, which means if I draw this little right angle triangle, this bit's 2, which means this bit is 1. This bit was RH, and this is R because it's the distance from the center of the sphere to the outside of the sphere. Yes! And so therefore, R squared minus RH squared is going to be 1 squared because of Pythagoras. Yay! And so therefore, this is minus a third u of 3 over 2, u equals r squared, u equals 1. Well, 1 squared, but you know. And this now does not involve RH, and we have actually solved the problem. I mean, we can finish it. So we've got minus a third times 1. Well, that'd be minus a third, wouldn't it? Plus a third times r squared to the 3 on 2. The exponents would multiply, I get r cubed. Cool. Is that the answer they got? I really hope it is. Oh, crap, we haven't done the other bit yet. Okay, nearly there. And this integral, we only just did this integral here. And the other integral from theta equals 0 to 2 pi of d theta, well, that's a 1, and so that would be theta from theta equals 0 to 2 pi, which would be 2 pi minus 0, which is 2 pi. And so therefore my v is 2 times the first integral, which was a third. Oh, crap. Has something gone wrong? But I did there was still a times minus a half there. Because of the substitution. Yeah, I'm getting there. That's the answer I've got, where r is the radius of the sphere. Oh, but r cubed. No. It's supposed to be independent of the radius of the sphere, isn't it?
No, the total volume minus the volume of the hole.
Ah. Oh, the volume of wood remaining. Okay. Okay, it's all good. So that is the volume that we removed. So when I actually did this integral, which is a whole separate skill, I noticed that this didn't involve any theta, so I could bring the whole integral out. And then I could do these two integrals separately. This integral I did with substitution. And then I noticed that I hadn't used the fact, I was getting annoyed at this thing. And I thought, oh, well, I haven't used the fact that the height is 2 yet, so maybe that'll help. Right. So the bit removed, just a second, the bit left will be the volume of the whole sphere minus the bit that we removed. Ah, look at that. R cubed minus R cubed minus 1 will be R cubed minus R cubed plus 1, which is just that. Oh, how cool is that? How are people feeling? Because I had a root and I don't like integrating roots. And I noticed that it was times by R, and the R is nearly the derivative of the thing under the root. So if I differentiate this thing, I'll get minus 2R, which is only a constant multiple off from just R. And so I called U this thing, which says to me that I probably could have parameterized space differently in the first place. Yeah. Okay, yep.
Just like clarifying the process. So you want to come up with a function that like rotates in between. So instead of the whole sphere, and then you want to parameterize the like area that you're specifically looking at.
Yep.
Find the points out, which is the root of.
Yep.
Okay.
I'm going to do another one just to really get this working. Okay. Those who are online, if I'm looking out into the audience and saying how you feel, that applies to you as well, okay? Just make sure that you give me comments or use your voice. Let's do this duck. According to Archimedes' principle, body sinks until it displaces its own mass of liquid. Paraboloid bowl with shape x squared, z equals x squared plus y squared. Water is density 1,000 kilograms per meter cubed. Okay. And how far does it sink? Oh, this second, it's got a weight 40 kilograms. Okay. All right. So So this is Archimedes' principle. So I need to figure out, all right, I know what this looks like. It looks like that. It's a parabola, because z equals x squared would be a parabola, and then I've rotated it around this way. And then the bowl will sink into the water. All right, which would be the same as saying that the water rises. All right. And the goal of this problem is to figure out what this depth is, how far it sinks. And I do know that once it's at this zone, the amount of water that has been pushed out the way is this amount of water here. And that volume is supposed to be worth 40 kilos once it's settled at that spot when it's sunk. So this is 40 kilos of water. So if each meter cube weighs 1,000 kilos, then this would be 40 divided by 1,000 meter cubed. Because one meter cubed is worth 1,000 kilos. So to know how many meter cubes fit in, I need to figure out how many lots of 1,000 fit into this. So I need to divide by 1,000. Yeah, okay. So that's the amount of volume of water that was displaced. So I need to figure out what the correct depth is in order to make that volume equal to 0.04 meters cubed if the distances are measured in meters, which I'm going to assume that they are. Okay, cool. I think I've understood the problem. I'm going to call this depth h. So there are many ways that I could set this up. Your lecturer has chosen to set it up by turning this picture upside down and making your bowl a hill instead of a bowl. Oh. Like that. So he's turned this bit here upside down and made it a height coming down instead of a thing going up to a particular height, because that made sense to them. I choose not to do that. It will come out the same. So this is a volume. It's a physical, literal volume. And so I could think of that volume as stacking up a whole lot of heights or depths, if you like. So what I could do is I could locate every point on this circle and figure out what the depth is at every point and add up all those depths, and that should produce the volume. Like times by the little bit of area that that depth is taking up should produce a volume. So this is what I'm imagining. Each point on the surface has a depth. Add up depths across the area, and that should produce a volume. That's what I'm imagining. So I need to locate every point in this circle and I need to figure out what the depth is at every point. And so the depth is what I'm going to put inside my integral, and the locating is what I'm going to do. It's going to be on the integral signs. So being a circle, it's probably easier to locate every point in there using polar coordinates. But just to be clear, I'm going to call this so the top of the bowl level with the water, I shall call disk D. And I need to figure out this is what I'm still imagining. It'll be the integral across the disk of the depth at each point times the area that depth is taking up. That's going to be the volume that I'm looking for. So I need to figure out what the depth is at each point. And I also need to figure out how to locate every point in this thing. So I'm going to just redraw my picture. So if this height here is h, this bowl had formula z equals x squared plus y squared. That's what they said the bowl's shape was, which means that if I'm here on the edge of this circle here, so if at this location, h is equal to x squared plus y squared, because that's the height, which is the z coordinate. And what that means is that the formula for this circle, the equation of this circle, should be x squared plus y squared equals radius squared, which means the radius is root h. So this circle has equation x squared plus y squared equals whatever the radius squared is, which means that radius must be root h because we've got x squared plus y squared equals h. And so radius squared should be h. How are you feeling? Okay. Okay. Let me see if I can explain why I made that decision. So I was looking at this. Are you okay with me making the decision that this is the volume I needed to figure out? Okay, cool. All right. So volumes can be made in two ways. They can be made, just as an aside, a new piece of paper, I'll come back to this working in a second. That's a really important question you're asking. So that's why I want to answer it now. All volumes can be made in several different ways. And one way to make a volume is to take a whole lot of areas and stack them up like that, which is how this stack of paper is made. A whole lot of areas that are all stacked together. And so the idea is that this area times a very thin sliced difference produces a volume if I add them all up. So the volume is the integral of the area times, and each area is times a little bit of thickness, and together all those little slices add up to a whole volume. Okay with that? There's another way to make a volume, and it is to say that you've got some area here, and every little piece of that area has a little slice on top of it, and together all of those slices produce the volume. which is a little bit more like me stacking up all of my textures like this together to make the volume of the thing. And so what this is that I have to have a height times a little tiny piece of area at the bottom. And I have to add them all up. But because there are two directions to move to get to every position on this bottom, it's a double integral. These are the two ways to make a volume. So this one requires me to know what the area is at every height, at every distance. So if I turn it this way, I can make an area at every height. This one requires me to know a height at every location in the area. Yeah, okay. So when I look at this, I could imagine this as being made of a whole lot of circular slices, which would be this picture. And each height has a slice that has an area, and I can go the area times the width, the tiny little piece of slice across the different heights. That would produce the volume. I could also imagine this being made up of a whole lot of thin sticks all glued together vertically to produce this shape. And so as long as I can figure out how long the stick is at every position on this thing, that will produce the volume. And that's how I decided, because I know a way of locating every point in a circle. And I also was told right from the beginning the formula for the Z given the X and the Y, which says that given a location in a plane, I'm told what the length of the stick is. So that was what told me to use this thing. Yeah. Is that okay? Yeah. Sweet. All right. So since I've made the decision to have a little depth at every position here, I need to figure out at every position what the depth is and how to figure out what that position is. So at the moment, I'm just figuring out what the top of the circle is because I don't know what anything else is going on yet. So I'm going to figure out what the edge of this circle is first, because I'm going to have to locate every position inside this circle, so I need to find the edge first. So I've been told that the height of this is z equals x squared plus y squared. So that tells me at the very top, h is x squared plus y squared. And if it was a circle, it would be x squared plus y squared's radius squared, so the radius must be root h. And if I want to locate every point on the radius of inside a circle of radius h, it will be the points in the disk will be r cos theta, r sine theta, where r is going from 0 up to root h because that's the maximum radius at this spot, and the theta is going from 0 to 2 pi. And that should locate every point on the top of this disk here. How are we feeling? So what I've now done is that this point has been located this way. And now I need to figure out what the depth is. So I do know what the depth is. I can figure out from the x and the y coordinates instead. So I know that the depth is this distance here. It's at height h. And I was also told that the shape of this bowl is x squared plus y squared. So I'm going to go down here to the edge. That height there, that is the x squared plus y squared. Because that's how high the bowl is above the bottom. That's what z equals x squared plus y squared means. And so the depth is the height minus the x squared plus y squared. But what I'd really like to do is I would really like to write that in terms of the r and the theta that I use to locate this point. And so what I'll do is I'll say, because that's how it works, x squared plus y squared is r squared when you use this polar coordinate thing. Okay. And also the dx dy is r times dr d theta because we figured that out earlier. Because in a technical sense, this is the point xy is equal to r cos theta, r sin theta. And so now my integral, which I wrote earlier, is going to become I've had this integral before. So the disk is now located by doing the radius and the theta. That's how we locate every point in the disk. The dx dy is now r dr d theta, and the depth is h minus r squared. And now I integrate it and it'll tell me what the volume is. So again, I notice this doesn't have a theta in it, so that's really convenient. If it did, then I would have to do something else. But I'm going to bring all of this out. That's because your lecturer, whoever wrote the problem, has given me something that's symmetrical in a circular sense. And this, I could so do it by substitution. That'd be hilarious. But I don't want to, because I can expand this out. And that, I'll deal with that later. So this will be, the h is a constant multiplied on, so it'll still be there. The power will go up by 2 and I'll divide by the new, up to 2, I'll divide by the new power. The power will go up to 4, I'll divide by the new one. And this will be theta from 0 to 2 pi. So this will be h times a half of root h squared minus a quarter times, that's not a pi, it's an h, times root h to the 4 minus, oh, if I put 0 into both of those, it comes out to 0, and times this by 2 pi minus 0, and so I get, okay, so root h squared is just h, so I've got a half of h times h, which is h squared, minus a quarter of root h to the 4, which is also h squared, times 2 pi. So I've got a half minus a quarter is a quarter. Which is pi h squared on 2. And this I need to be 0.04. Because that's what we figured out right at the beginning. And so therefore h squared is 0.04 times 2 divided by pi, and h is whatever the square root of that is. Which I don't care to figure out. Where's my phone? Not that you can use your phone in your exam, but square root of 0.04 times 2. Okay, there we go. 16 centimeters-ish. Right, so this bit was the trying to match up with the actual problem they gave us, which was about sinking. But the integral itself was this bit here. So you have to reuse the techniques of integration that you know for that bit. And how do we feel about the setting up of the interval in the first place? Yeah, cool. I've about 10 minutes till the next one. Do you want me to talk about anything else? Yep.
Can you do a, well, we've got 10 minutes, but a quick run through of how to do maximum minimum thing with Taylor series for second order?
If I knew that off the top of my head, I could do that. So when you say maximum minimum thing, you mean finding where the maximum minimums are and whether they're maximums or minimums?
Yeah, well, find the critical points based on Taylor's theorem, multivariable, action up to second order, and then depending on what the last term is, it's plus, minus, or all pluses, or then it's
Oh, that's because it's the wrong file.
then the second order term is positive and negative, and from that we can infer what type of critical point it is.
This thing? Because this is second order. So this is for a function of two variables. Did you do it for any other size things? Sweet. So this was technically a Maths 1B. They didn't do the Taylor's theorem thing, but they went straight to here. And so you're wondering what's this with the big one, with lots of. Oh, now we're into something else. Sorry? Okay, so we want to go previous. Let H be the Hessian matrix for a C2 function defined on a subset of Rn. Determinant of Hi. So Hi is the matrix at the top left corner. There's a lot of words there. So am I right in thinking that these notes don't have an actual example of this with 3 variables? But you're expected to do it with 3 variables in one of the assignments? Fabulous. So presumably it was in one of the tutes? Okay, I'm just going to read what it says here. The thing that is bothering me at the moment is it doesn't directly connect it to things. So it says here that, let me just step back a bit. Taylor's formula at the second order reads this. So you have the function value and the derivative times, the derivative of f at the point, which will be a number. No. Okay. And then half of this thing. But because it's a critical point, this bit's 0. Oh, cool. Nice. Okay. Okay, just a second. It says that so f of x is a number. Yep. It's a number, right? This is it, yep. And this is in Rn. And then f of x plus h. So a critical point the derivative of f at that point is 0. Yep. Okay. In every direction. Okay, cool. And so we get that. Like that. That's what it said. Yeah. Because this is 0 at a critical point. So this is always true, but at a critical point, that's 0 and we get this. Okay, so this is telling me that if I move in the direction h, then the function value will change in this way, approximately. That's what this says. So f of x plus h is the function value at x plus this much. And if every direction that you move, you go up, like if this is always positive no matter what h is, then this must be a minimum. Because if I was here at x naught and I moved h this way and the function value went upwards, then this would be a minimum. And if every direction I went, the function value went downwards, then this would be a maximum. So if this number is, so this is the idea. So if x naught plus h is approximately to f of x naught, I just wrote it again. If this is always positive, if this is always positive no matter what direction h is, because h is a vector, then f of x naught plus h is always more than f of x naught. Because it's x naught plus a bit. And so therefore f of x naught is a minimum because everything nearby is bigger. Well, I'll deal with that in a second. Okay, so what we've discovered here is that if h transpose h is always positive, then that will make it a minimum. And if h transpose h is always negative, then that will make it a maximum. And any other time, it won't be either. It'll be some sort of saddle point. Okay, so then the notes say that Sylvester's criterion says that if the determinant of all of the, if the determinant of every smaller matrix from the top left of this big matrix H is always positive, then H transpose H will always be positive. That's what that says. I'm just going to write that down. And they're saying that det HI is negative for the odd ones and positive for the even ones. Then that will mean that H transpose HH will be always negative. Okay, that's what Sylvester's criterion says. You can't see me writing, but that's fine. So this is what I've written. The determinant of HI is positive for all the i's, and that means that this is always positive. And that says that it's a minimum. And this being negative for odd I and positive for even I means that this is always negative, and that means that this is a maximum. And if neither of those things happen, then it's neither a maximum nor a minimum, and therefore probably some sort of saddle. I don't know. Something about matrices. So I don't know the details. Yep. Proof beyond the scope of the course. Therefore, I've never seen it. So I can look at this. If the Hessian came out to this, then it's not going to be a maximum because this one's positive. Because this is an odd one here, like that's H1. So, yay! That would be my very first interpretation of this. So if it was going to be a maximum, that would have to be negative. But you'd also need this determinant to be positive and this determinant to be negative, and then we'd know it was a maximum. But if all three of those were positive, then it would be a minimum. And if neither of those things happens and it was some other combinations of positives and negatives, then it would be neither, and it would probably be some sort of saddle point. It's probably something to do with just determinants, and I don't know. I'm sorry, I just don't know enough about how matrices work in this context. Yeah. I really am going to stop there.